All right, so welcome back. It is my pleasure to introduce the first speaker of the afternoon, Alessio Figalli from UT Austin. He will continue with his third lecture, speaking about flow of non-smooth vector fields and applications. Please, Alessio.
Okay. So, thanks a lot. So maybe before, as I mentioned yesterday, today I would like to discuss a bit about the Vlasov-Poisson system. But before doing that, I will make just a few more comments about what I did in the last two lectures. So basically, all the purpose was the following. So let's say I have a vector field, again, Bt from Rn into Rn. For simplicity, I always assumed that my vector field is divergence free. And the goal was construct a unique flow, what we called regular Lagrangian flow, which has the property that solves that this map capital X, the flow, solves the ODE, and in addition is incompressible. Now, the approach that we used, so the approach was basically an a priori estimate. So what we proved is that if Bt, let's say, is L infinity and is W 1p loc and p is greater than 1, then the flow, and you assume also, so if you assume in addition that this is smooth to make sure that the flow exists, then the family of such a flow, such flows, so the family of flows generated by vector fields of this form is pre-compact in L1, right? We provided a compactness estimate in L1, which allowed us to prove existence just by approximation. You regularize the vector field, and then you pass to the limit. So this works well in this setting. You can do this also. So this approach is OK also if the vector field is Bt is W11, or Bt is something like some density, let's say, h of t, convolution with the gradient of the fundamental solution of the Laplacian, where h of t is in L1. So we'll say this is very similar to what happens in Vlasov-Poisson system, that kind of vector field that arise. The problem is Vlasov-Poisson is that in general, maybe you may have problems here. So L1 is not a good functional space. Family of functions which are bounded in L1 may not converge to something in L1 because they may concentrate and produce a singular measure. So L1 is not reflexive, so bounded sequences in L1 are not compact. You may create singular measures. And this is a problem in the sense that if you put a measure here, no one really knows how to deal with that. So the approach for Vlasov-Poisson is not by approximation. So here I'm proving too much. For Vlasov-Poisson, proving really pre-compactness of the flow with such a clean estimate is not what one can really do. And what one has to do is something which is a bit intermediate between what I did in these two lectures and what Luigi did last week. So maybe just very briefly, let me explain what I mean. So just as a reminder of the techniques, but just 5 minutes, and then we move to Vlasov-Poisson. So another approach, alternative approach, is the following. So you don't work by compactness. You say you want to exploit the PDE. So you have on one end, you have the ODE x dot equal Bt of x, let's say at time t. On the other end, you have the continuity equation, let's say dt rho t plus divergence of Bt rho t is equal to 0. Okay, so we have the ODE on one side and the PDE on the other side. Okay, so you don't know how to deal with that, so let's move here. The PDE is much easier in some sense, at least for existence. So consider an initial datum, rho 0, which is something, you want something equivalent to Lebesgue. But let's make it finite measure to avoid the problem. So let's say rho 0 is a Gaussian. So rho 0 is e to the minus x squared over 2 dx. Just something equivalent to Lebesgue, which has finite integral. So let's take this, and now you want to solve the PD with vector field, with our vector field, BT, vector field, BT. So this is very easy. You don't need anything. Let's say L infinity is enough. You don't need any regularity to solve this PD. The existence is easy. Why? Just by convolution. What you do is that, so to construct a solution, you consider BT epsilon, which is BT convolution some phi epsilon, to make it infinity. So now I have a infinity vector field. And now you solve dt of rho t epsilon plus divergence of b epsilon t rho epsilon t equals 0. So this one we know how to solve it because, so remember this is divergence free, so it's transport equation. So the formula is given by rho epsilon t at the point x is nothing else than rho 0 at the point x epsilon t minus 1 at x, right? So you transport the value, right? So you have, this is the time t, this is the time 0. If you want to know the value here, you just use the flow. I denote by x epsilon the flow associated to the vector field b epsilon, which exists because this is a infinity vector field now. And I have my solution for every time. And now you notice that rho 0 is like a Gaussian, so it's bounded by 1. So all these densities are bounded by 1 pointwise. So they're in an infinity uniformly. So we have that rho epsilon t is uniformly in L infinity, uniformly with respect to epsilon. So if you have a sequence of bounded function, up to subsequences, they converge weakly star in L infinity to something bounded. So rho epsilon t will converge weakly star in L infinity to some density rho t. In addition, the vector fields b epsilon t, because these are done by convolution, they converge to the original vector field strongly in L1, because convolution limit, I mean, when you convolve, then you have strong convergence there. So then you just write the PDE in distributional form. So you know that the fact that rho epsilon is a solution means that for every test function, let's say psi, C infinite and compactly supported, you have that the integral of rho epsilon t, so you integrate by parts the derivatives, times dt psi plus b epsilon t times the gradient with respect to x of psi rho epsilon t. Let's say from 0 to, so this is in Rn, and let's say this is from 0 to t. So C infinity in 0t cross Rn. This is 0. I just integrated by parts, right? You take the PDE, you multiply by psi, and you integrate by parts. And that's what you get. All the derivation from psi. Now, this guy converge weakly star to rho t. So the product converge is this against a smooth function. And now this one converge weakly star to rho t. But this one converge strongly to bt. And this means exactly, so everything passes to the limit, no problem. Because weak and strong convergence together, they go well. And then we are happy. We have that in this sense of distribution, dt rho t plus divergence of bt rho t is 0. So this is to say that the existence for the PD is easy, just approximation. Now, what is the next step? So this means that I have my Gaussian, my Gaussian density, and then, so this is at 0, and then I have an evolution in time. So my density evolved, rho t. So this is the direction of time. Now, in general, we don't have trajectories. Our vector field is, at the moment, vector field is just bounded. Okay, just bounded. The only thing is divergence free, but it's bounded. But there is this general superposition principle that was stated by Luigi last week that tells you that if you give me a solution to the continuity equation, there is always kind of a generalized flow behind it. So you don't have a map, but you have a kind of probabilistic representation, a kind of probabilistic representation of your solution, which is the following. So there exists this so-called superposition principle, which tells you the following. There exists a measure eta, which is a probability measure in the space of continuous function from 0t into Rn, so in the space of curves. So there is a probability measure in the space of curves such that two things happen. One, for eta almost every gamma, so this is a measure in space of curves, so our points are curves. Gamma dot is equal to bt of gamma, so almost every curve solves the ODE. And second thing, basically if, so this is a measure in the space of curves, so basically I have a family of curves here, and maybe there are multiple curves leaving from the same point, and maybe some curves can merge and keep going together and then branch, separate again. So this measure lives in the space of these curves. It gives me a weight to every curve. And what happens is that if you look, so basically this measure push forward your initial measure, rho 0, to rho t. What does it mean? It means that, so heuristically means that if you look, you take the measure rho 0, and you let it flow using the curves on which this measure eta lives, and you look where is the mass at time t, then you get rho t. And this is written the following way by saying that for every test function psi, the integral of psi in d gamma t, so if you evaluate psi at all points gamma time t with respect to d eta of gamma, so this is the integral over a space of continuous curves in Rn. This is the same as the integrating psi of y with respect to rho t of y. So this is a way to represent your, so what this formula is telling you is that if you look at this measure eta and you look what happens at time t, the mass is where is compatible with rho t in some sense. So eta at time t is exactly sending the mass, the original mass rho 0 at rho t. So just to give an example, so if there exists a flow, if a flow exists, if a flow x exists, then you can write the eta in the following way. Eta is kind of a tensor product, so for every x here, you have the measure rho 0 of x dx. So this is a weight for the initial position times tensor product with the delta concentrated on the trajectory starting from x. So basically, another way to say this is that for every function, now capital psi, from the space of continuous paths in Rn with values in R, the integral of psi of gamma d eta of gamma is the following. You integrate psi along this trajectory So these are psi which to every gamma associated a number, and then you integrate this with respect to rho 0 of x dx. And what I'm doing here, so if you take now psi of gamma equal the value of gamma time t, so the map that to every gamma associates its value at time t, then here you see that the integral, this becomes, let's take also a test function. So psi of gamma is some other function little psi of gamma of t. So then this becomes psi of gamma of t d eta of gamma on the left. And on the right, this is the integral of psi of x t little x rho 0 of x dx, which is the formula we're a bit more familiar with. So you see that then if you compare this formula 2 with this one, what we are saying is that the integral of psi capital X of tx rho 0 is the same as the integral of psi rho t. And so what we are saying is simply that xt push forward rho 0 is rho t. So that's exactly the push forward condition, just in an abstract way. And so this may look a bit heavy as a notation, but basically it's the only thing you can do. That's life. But the crucial thing is that this guy always exists. So maybe a flow doesn't exist, but this guy always exists for non-negative measures, for non-negative probability measures. And so, okay, I say that there's a probability, in fact, so maybe just here you should pick a renormalization constant to make this probability, to make sure that everything is a probability measure. And then what you do, once you have this measure, so basically this measure gamma, you should think it philosophically in these ways, right? You have rho 0, you have rho t. For every point x, maybe there are multiple cars which exit. Maybe there are cars merging. But these cars tells you how the mass is transported. So eta, this measure eta tells you which cars you are using to transport the mass. OK, so now you can always write, so given now eta, you can always write it in the following kind of tensor form. Eta of x tensor rho 0 of x dx is the analogous of the previous formula. Basically, you do the following. You say, OK, I have a measure on the space of all cars, but let me decompose it I just consider these the cars. So these are all the cars that are at x at time 0. So you only consider that cars. Okay, so and you write your eta as a superposition of all of these. So your eta is a measure in a space of a lot of cars. So you just say, okay, let me kind of disintegrate this measure as a superposition of measures. And each measure is concentrated only on cars starting from x. Okay, so this is that's the analog of the formula before. And then the analog of the computation I did yesterday would be the following now. The kind of quantity you want to do for Vlasov-Poisson is this. You take the integral over the ball of reduced R, and now you have the log of 1 plus, maybe you remember we used two flows, x1 and x2 we put in the formula here. Now I'm going to put two cars, gamma minus gamma tilde divided by delta. And then I integrate d with respect to d eta of x of gamma, d eta x of gamma tilde, and then in dx. So rho 0 of x dx. Well, let's put, yeah, well, it's the same. Rho 0 of x dx. So this is the kind of integral I do. So I integrate also with respect to cars on which gamma is concentrated. Now, if eta of x was simply the delta at the flow, then this is what I'm writing here. So this measure is a measure concentrated on a family of curves that exit from X. If there is only one curve, then I have gamma can only be capital X. I have only one choice. Gamma tilde can also be only capital X, because these are two deltas. And so here I have X minus X, which is 0. Okay, this is 0 if and only if these curves are always the same. So imagine, for instance, let me do an example. Assume that eta of X was this, was 1/2 the delta at x1 of X plus the delta at x2 of X. So suppose that for every X, I had two flows exiting. Right? Then what is this integral? Okay, you have to integrate. So here you have to take a curve gamma respect to this measure. So either with probability 1/2 you get this curve, with probability 1/2 you get this curve. Okay, so if the first eta takes this curve, here you put x1. Now, if there's also the second eta takes this x1, you get x1 and x1, and you get 0. So basically, here you have 4 terms, depending on which curve you pick here and which curve you pick here. Basically, this is nothing else than the integral of the log of 1 plus gamma minus gamma prime over delta with respect to the measure. So what do? 1/2 of the time you take, So what do? 1/2 of the time you take the first gamma has to be x1. So I put x1, this happens 1/2 of the time. Now, for the second one, 1/2 of the time I take gamma tilde also to be x1. And then I get 1/4, 1/2 and 1/2. So 1/4 of the time I take x1, x1, plus 1/4 of the time I take the integral log, and then I take 1 plus x1 minus x2 over delta. Because I take, for the first gamma, I take x1, but for the second gamma tilde, I can take x2. Then another time, I take x1, x2, x2, x1, which is the same. So you get this 1/2 of the time. And then another 1/4 of the time, you get x2, x2, which is 0. This is 0. And so the only term left is this. So that's just to say that this is nothing else than a generalization of considering two different flows associated to the same vector field. So this is like a more general construction. So you look at this function, you do the computation, you differentiate in time, you do all the argument I did yesterday. Of course, for Vlasov-Poisson, it becomes more technical because you don't have the same harmonic analysis estimate. And then a posteriori, you prove, so after you do the whole computation, you prove that gamma equal gamma tilde almost everywhere. So the two curves, eta x almost everywhere. Which means that for eta of x, so for almost all curves on which eta lives, all the curves are the same, which means there is only one curve. Which means that eta of x is the delta along some curve gamma of x, which means I have a flow. I have a flow because for every x, there is a unique curve. So I have a flow. I don't have division. So this is a different way, a different path to prove existence of a flow. So actually, sorry, existence and uniqueness, of course. And in some sense, it's more flexible, although I understand that it's more heavy in terms of notation, because I'm not proving compactness. So it's the difference between proving that something is stable with respect to something is unique. I'm not trying to prove that there is a stability here. Just claiming, you give me this object, this is single valued. So it's a weaker statement than the compactness of the flows that I proved yesterday. Okay? So this is basically what I did in this 15 minutes is a summary, if you remember, of also what Luigi did as an approach. In his case, he didn't use this part. He was using the PDE. but the strategy is the same. So what I'm doing here is a combination of what Luigi did and what I presented. So I finish here with this part. It was just to tell you that there is much more behind if you want to really apply it to Vlasov-Poisson or the kind of equation where the vector field is more singular than W1P. And you have to pass through this machinery. I don't know how to do this without using superposition principle or stuff like that. So that's kind of needed. OK, so now we can forget all this, and we can move to Vlasov-Poisson. So what I would like to do today is just kind of an overview of the PDE. I would like to show you maybe some basic estimates, conservation of energy, and some a priori estimate for solutions. So we need to follow my notes because today we'll do a lot of older Sobolev embedding for functions. So what is Vlasov-Poisson? So Vlasov-Poisson is related to the following system. So you have a family of particles which are represented by density. So this is Ft of xv represents the density of particles that at time t are at position x with velocity v. Okay? So these are density distribution of, so these are non-negative because it's a density of particle. And it represents how many particles you have at fixed time in some position with some velocity. Now, associated to this, you can define a charge density, rho t of x, which is by definition the integral of ft of xv with respect to dv, the v variable. So this is so both variables lives in Rd. So this is the integral over Rd. And this is the density of particles that at time t are at position x. Okay, so you forget about the velocity. All you look maybe at some point, at some time you have multiple particles, and maybe just that here you see them different because they have different velocity. Here you forget that they have different velocity. They all collapse together. Now, this is the real density that represents kind of the physical the particle in the physical space. Tells you the particle at position x. So this is the density which generates a potential in the space. So I will consider two kinds of potential, which is either repulsive or attractive Coulomb potential. So you have a potential, the sign will never be good. So Vt of x, which is minus sigma times the convolution of rho t with the Coulomb potential. Okay? Now, sigma can be either +1 or -1. So there are two possible signs. +1 corresponds to the repulsive case. So repulsive, so this is charged particles. You take two particles who have the same charge, they're going to repulse each other. Or attractive, -1. This corresponds to the gravitational case. So in gravitational mechanics, particles always attract each other. So depending on the sign of sigma, you have two different dynamics. Usually, so the repulsive is always easier than the attractive. We'll see it because in some sense, in the repulsive, people try to stay far away from each other. And that's good because your density will not concentrate too much. In the attractive case, the density can increase more because of this attraction. And then, so this is the potential. And associated to a potential, you have an electric field, or let's say a force, Et of x, which is minus the gradient of the potential. Okay? So this is the force generated by the potential. Okay, and by Newton equation, what do we have? We have that the derivative of the position at time t is equal to the velocity, and then the derivative of the velocity, which is the acceleration, is minus the gradient of the potential, because that's the force. So this is the electric field. Okay? So I can see this as the following ODE, little x, little v dot equal the vector field bt of x and v, which is v et of x. Okay? So this is the ODE, the Hamilton equation. And so this is my ODE. And now what is the PDE associated? So my density of particles will move according to this ODE. So, and this is, okay, let me observe that the divergence of BT, what is this? So you have to take the divergence with respect to the x. So these are the first D component. These are the second D components. This lives in x, this lives in y. Right? This corresponds to x. So when you take the divergence, this is the divergence with respect to x of v plus the divergence with respect to v of et of x. And this is 0. V doesn't depend on x, et of x doesn't depend on v. So these are divergence-free vector field. So you can interchange continuity or transport equation. And so the evolution of the particles is given by dt ft plus divergence of bt ft equals 0. This is equivalent also to dt ft plus bt times the gradient with respect to x and v of ft equals 0. And now if you write explicitly the vector field, this is the usual way to write Vlasov-Poisson. You get the first component of the vector field is v with grad x. And the second component of the vector field is t of x with grad v of ft. And that's 0. So you have a transport equation where this part of the vector field depends on the solution itself through that identities. So you have to define rho t of x to be the integral of ft of x v dv. And then et of x up to a constant that I will always forget. When you take the gradient of this potential, d minus 2 pops out. But let's forget the d minus 2. So up to a constant is sigma. And the integral of rho t of y x minus y divided by x minus y to the d dy. So this is the gradient of the gravitational potential. This is the vector field, the electric field. Okay, so this is Vlasov-Poisson. It's called like this because this is the so-called Vlasov equation, which simply corresponds to the evolution of our density ft using this Hamiltonian vector field, just Newton's law. And it's called Poisson because the vector field is recovered through the Poisson equation. We are solving, so this, here we are solving the Laplacian equation. Laplacian of Vt is sigma rho t, minus sigma rho t. No, sigma rho t. Whatever. I will always mess up with signs, but I will try to be careful. Okay, so this is thus the inverse of the Laplacian, so the Poisson equation. Okay, so we got the ODE, we got this, and maybe, okay, now I can talk about this. So let me talk about what kind of solution one would like to consider. Usually for transport equation, continuity equation, the notion of solution is distribution, okay? So definition would be ft is a distributional solution. Distributional solution. If you integrate by parts in the equation, right? So you have the double integral, let's say, of any test function psi, so dt psi times ft plus you integrate by parts all the gradients. So you get v times grad x psi f of t plus et of x times grad v psi f of t equals 0. right? Let's say from 0 to t, and this is in Rd cross Rd. So you have the integral in space, time, and velocity for every psi, which is, let's say, C infinity and compactly supported. Okay? So usual distribution definition, integrating by parts. So here I used the fact that my vector field is divergence free, and this is very convenient because that's what allowed me to integrate by parts. Right? Okay, so this is the definition. And now immediately you see a problem. So when you have the definition, so when you consider solution in the sense of distribution, you have to be able to compute an integral. You're integrating here, right? So you want these objects to be integrable at least. Now, okay, ft, let's say, is very natural to assume that, say, that ft is L1. We'll see that this is very natural, integrable at least. So this is L1. dt psi is infinity and compactly supported. This is nice. Now, ft is L1, and then this is infinity and compactly supported. And also v is bounded because we're only integrating this function on the support of psi, right? So if we are in the phase space x and v, let's say psi lives here, and so where psi lives, v is bounded. So this is a bounded function. This is L1, the product makes sense. Now here the problem comes because, okay, this is nice, but I have a product of ET with FT. And ET depends on the solution itself, so it's not clear whether the product is still L1. Okay, so this is an issue. So both functions, they're both L1. I mean, this is okay because, so the remark, of course, is that ft, let's say in L1, implies that rho t is in L1, just because the integral of rho tx dx is nothing else than the integral of the integral, use just the formula, of f x dv. So you substitute the definition of rho t, and so you see that the L1 norm of rho t is the same as the L1 norm of f. So if f is L1, rho is L1. The problem is that we're going to see this later, but FLP, even p greater than 1, the only thing that implies is that rho t is in L1. You don't gain integrability. And I'm going to discuss this later, but let's believe this for a second, okay? So rho t is only L1. So what can I say about the vector field? So the potential, so what do I know? I know that the Laplacian of the potential up to a sign, now I will always break on this, is rho t. Okay? So this is only L1. So the Laplacian at most gains 2 derivatives. So this implies, even if, so this is false, but basically Vt is W to 1. This is false because the Laplacian doesn't work for L1, but better is almost W to 1. So which implies that at most Et will be W11 because Et is the gradient of Vt up to sign. So L1, we gain 2 derivatives, we lose 1 derivative with the gradient, you are W11, and W11 embeds in L d minus 1. Okay? So this implies that if I want Ft Et to be L1, let's say L1 lock, by Holder inequality, how do you prove that the product of function is L1? You apply Holder, right? But to apply Holder, you need this to be conjugate exponents. So since Et, we know that is in L d over d minus 1, then what is the conjugate exponent of this? We need Ft basically to be Ld. Ld is the dual space of d over d minus 1 if you do the Holder conjugate, right? And so it means, so okay, this is, here I cheated a bit because you don't really gain exactly this. So in fact, what you need is a bit more. So Ld should be Lp, and p should be greater than the dimension. Okay, so this means that to give some meaning to the product, you need some kind of higher integrability on F. FL1 doesn't make sense. Okay, so this is, one could say, okay, in fact, yeah, I don't care about putting these kind of assumptions. I put higher integrability on F, I'm happy with that. But, I mean, this is not necessarily a natural assumption. And we're going to see later, anyhow, that even if you put L infinity, there are still problems in any case, depending on the dimension. So let me also make a comment. You see, the bigger the dimension, the bigger you need this exponent. So Vlasov-Poisson is very dimension dependent, because basically you always apply elliptic regularity theory and then Sobolev embeddings. And of course, the higher the dimension, the worse are the embeddings. So in fact, things go well only in low dimensions. So this was a first comment that shows that in general you can talk about distributional solution. But so what the observation, so maybe let me put it here, remark. So let's write the equation in non-divergence form. So dtft plus bt grad ft is 0, right? I can write it another way. Now multiply this by beta prime of ft. We already saw this both in Lord's lecture last week and in Luigi's lecture. So you multiply by a derivative of some function, beta prime composed with ft. And then you notice, when you multiply this, so that dt of ft times beta prime of ft is the same as dt of beta of ft by chain rule. And the same is here, at least formally. So this is a formal argument. So this implies that dt of beta of ft plus b capital T of grad beta ft equals 0. So if ft is a solution, beta of ft is a solution for every beta from R to R, let's say of class C1, because I need beta prime. So. Okay? And now I can use that the vector field is divergence free. So I get the dt beta of ft plus the divergence of bt beta of ft. This is 0. So beta of ft solves this continuity equation. So beta of ft, now I can talk about distributional solution for beta of ft. So now I can multiply by test function integrated by parts. So I get that the integral of dt psi beta of ft plus v grad x psi of beta of ft plus et grad v psi of beta of ft is 0 for every psi C infinity and compactly supported. Okay? But now, so if we assume now that beta is both C1 and bounded, I can assume it. Just think beta, for instance, I don't know. So beta could be a nice bounded diffeomorphism or R, for instance, arcotangent of, well, this is not arcotangent, but something like this. Or like this, whatever it is, for instance. Then automatically, for free, beta of ft is always L infinity, just because beta is bounded. So beta composed with ft composed with beta is bounded. And this implies that then et times beta of ft is in L1 lock, because this is L1 lock, and this is bounded. So the bounded term now is for free. So if you, instead of looking at the f of t, you look at functions of the form beta of ft, no matter what is beta, as long as it's C1 and bounded, then the equation makes perfectly sense. And this is what the DiPerna and Lions introduced at the end of the 80s. So they gave this definition. This is due to DiPerna and Lions in 88, roughly. They say that f of t is a renormalized solution of Vlasov-Poisson if for every beta from R into R, beta which is both C1 and bounded, beta of Ft is a distributional solution. Of Vlasov-Poisson. Okay? So they only require the PDE to be satisfied by beta of Ft. In this way, they don't have the integrability issue. So I'm going to come back to this later on. So in fact, this is in general, if you don't want to assume some strong assumption on the initial data, like big LP or L infinity or something, this is the definition of solution you need to consider. There is, I mean, that's unavoidable. Distribution solution doesn't make sense. Okay, so now I would like to play a bit with the equation and to show you a bit some of the features of this PDE. This way, I will also come back to the point that I mentioned before when I say that even if F is in LP, you can't get more than L1, only with integrability of F. Okay, let's do some a priori estimates. So I will start to, all I'm going to do now are going to be formal computations. So you can think that I have smooth, nice solutions, and you do everything. Just for your information, global smooth solutions are known to exist in dimension d less or equal than 3. And there is no uniqueness known at the moment. But the existence of global smooth solution stops in dimension 3. And this is a paper, dimension 3 is due to Lyons per Tam, around 91. There are some criteria for uniqueness of Vlasov-Poisson, but basically no one is able really to prove that these criteria are satisfied. So there is no uniqueness basically, except some results in one dimension. And the global existence of smooth solution breaks down in dimension 3. So in a dimension higher than 3, nothing is known at the level of smooth solutions. Okay, so now let's, okay, this was just for information. Let's start to do some formal computation, understand what kind of properties one can hope to hold. So, formal computation. Let's put it another way, a priori estimates. So the philosophy is, if a smooth solution exists, then it's going to satisfy the following properties. So the first thing is that d over dt, so for every beta, d over dt of the integral of beta of ft, this is the divergence with respect to x, and, well, with respect to everything, of beta of ft, right, by the equation. And this is the integral on the whole space, Rd cross Rd. And if I have a nice smooth solution, the integral of the divergence on the whole space is 0. Right? So if the solution decays fast enough at infinity. So this is 0. So this implies that every function, so the integral of every function of the form beta of ft formally is conserved. In particular, if you take f of beta of t to be, beta of s, t is a bad notation, to be s to the power p, then what you get is that d over dt of the integral of ft to the power p is 0. So all LP norms are conserved. Okay? So if you assume that at time 0 you have some bound, L1, L2, LP, whatever, this is propagated in time. Okay, so this is the first one. Now, this is an Hamiltonian system. So if you have an Hamiltonian system, you know that usually for Hamiltonian system, the energy is conserved. Right? The energy is kinetic energy plus potential energy. This is not completely true. This is true only if your potential is time independent. So if you take kinetic plus time independent potential energy, then the Hamiltonian is always conserved along the trajectories. Okay? In our case, the potential is not time independent because it's the convolution with rho t. So for Hamiltonian system, so if I have like an ODE of the following form, x dot equal v, d dot equal minus grad v of x, then d over dt of kinetic energy plus potential energy, this is identically 0. Right. This is a standard computation. Obvious. So this is conservation of energies along trajectories. But this is true only if your potential is time independent. Because if your potential is time dependent, you have an extra term coming from differentiating the potential. In our case, Vt of x is what is minus sigma rho convolution 1 over x to the d minus 2 rho t. So this is time dependent. Okay, so a priori this doesn't go well with the conservation of energy. But because the potential depends on the solution itself, there is a magical cancellation. And in fact, you don't do exactly kinetic plus potential. You do 1/2 kinetic. So kinetic. You do kinetic plus 1/2 potential energy, and this works. There is a symmetry and a magic cancellation. So let me show you conservation of energy. And this works only because I integrate the Hamiltonian with respect to all the density. It's not pointwise along the trajectory that the Hamiltonian is conserved. It's only when you do the integral of everything that you get 0. So we are going to consider the kinetic energy, which is the double integral in so Rd and Rd of 1/2 d square f of t xv dx dv. And then we have the potential energy, which is the integral over Rd cross Rd of Vtx times ft of xv dv dx. That can also be written as the integral. So you can integrate in dv here, you get rho. So here you get the integral over Rd of Vt of x, rho t of x dx. The same. Let me remember. Okay, no. I don't want to call this the potential, I think. Oh, yeah, I would like to put a minus sigma in front, probably. Okay, let me put. 1 second. I'm undecided whether if I do it this way. Well, okay, let's keep this notation. Okay, so this is kinetic, this is potential. V was that. Yeah, so sorry, I'm confused now by the signs. Probably I want a minus. So this is not the right sign for me. Sigma equal. Okay, I'm just confused by the sign. For some reason, I want a minus. So probably here I'm doing something wrong with the signs. Or just the sigma is a matter of sigma. Let's do the computation, then it doesn't really matter much. So I'm going to consider this. So what I want to consider is a sum of kinetic and potential. So let me put a sigma. Yes. And so the total energy minus sigma minus. No. The energy the energy for me should be this. The integral of 1/2 v square ft dx dv. I want plus sigma. I think this is correct. We'll check over the computation whether I need a plus or minus. And then I do the integral of, so let me do in this way, k convolution rho t times rho t, where k is 1 over x to the d minus 2, which up to assign the sigma corresponds to the potential energy, right? Because the potential was basically that. So I got confused because I always did the computation the other way. So this is my total energy that I want to consider. Sorry, and now I have to divide by 2. That's the catch. So let's compute this energy. Let's see that why this is conserved. Modulo design. So I differentiate in time. So I have d over dt of e of t. This is the double integral of 1/2 v square dt of ft, integrated, of course, dx dv. And then I have plus sigma over 2, the integral, and then I differentiate either this or this. Okay? So the first time I get k convolution dt rho t times rho t, and the second time I get sigma over 2, the integral of k convolution rho t dt rho t. Okay? But now the property of the convolution is that the convolution, you can move it from one piece to another. So this is the same. Maybe let me erase this just here. So k was 1 over x to the d minus 2. I can move the convolution on the second piece. So this is the same as the integral of dt rho t convolution k. Okay. And now you see why I wanted 1/2. Well, you don't see it yet why I wanted 1/2, but I want 1/2, 1/2 because I have twice the same term, and this simplifies. So then this energy is equal, so the double integral of 1/2 v square, and then dtft is what? Is the divergence with respect to x of v ft with a minus, sorry, minus the divergence with respect to v of et ft, so here there is a minus, dx dv, and then the second term is plus sigma, the integral of k convolution rho t dt rho t. Okay. Now, what happens? Let me maybe discuss dt rho t for a second. So you take dt of ft plus divergence with respect to x of v ft plus divergence with respect to v of of et ft, and this is 0. Okay. And now let me take this PDE and integrate all of these with respect to dv. What do you get? So here, when you integrate in dv, you get dt of the integral of f. You get dt of the integral of f in dv, but this is exactly rho t. When you integrate here, the divergence is with respect to x. The integral is in dv, so they commute. So you get plus the divergence with respect to x of the integral of v ft in dv. And then the last one, you integrate the divergence with respect to v over the whole space in v. The integral of the divergence is 0. And so you get 0. The last term integrated on the whole space gives 0, because there's a divergence in v. So you discover that dt rho t is the divergence of this vector field. Okay, so let's go on with the computation. So I get equal. So here, I do integration by parts, the divergence. The divergence with respect to x, you integrate by parts, becomes gradient with respect to x of this, which is 0. And then you have divergence with respect to v here. You integrate by parts, and you get the gradient with respect to v of v square. And so you get the integral of v, so the gradient of v squared over 2 is v, times this, et ft. Okay? Plus sigma, and then the integral of k convolution rho t times dt rho t, which is actually, sorry, minus then the divergence with respect to x of the integral of v ft dv, integrated in dx, while this is dx dv. Okay? Okay, now I integrate this divergence by part here, and then I get equal, so integral of v times et ft plus sigma, the integral of gradient of k convolution rho t from this times v times ft, and then again dv dx. Okay, and now you see where all the signs come, because if I'm not wrong with definitions, so I defined et, if I didn't do it incorrectly, should be minus sigma gradient of k convolution rho t. Is because is the gradient of the is minus the gradient of the potential, and then you get that this is exactly minus this, and so the sum is 0. So there could be somewhere a sign mistake. Maybe there could be a plus here and then is a minus there. I don't know, but modulo. So if there is a sign is wrong here, one has to change the sign here, which actually is more coherent with what I did. So v was that. So that's what v was. Wait, what is v in my definition? Sigma k convolution rho. Okay. Here was the mistake. Okay. V is that. Now I'm happier. Now it's correct. Okay. I just copied it wrong. So the mistake was just in the original sign of Vt here in this formula. So here I put the minus sign, which was bothering me all along, but in fact it's with a plus. So this is the right formula for V. And in this way, Et is in fact this. And everything is perfect. This is exactly the potential energy. This is exactly now 1/2 the potential energy. And this is the kinetic energy. Okay, now I feel better. Okay, so you see that what is conserved is not kinetic plus potential, it's kinetic plus 1/2 potential when you integrate everything. Because you need this 1/2 to cancel with the fact that you have two terms here. And basically this takes care of the fact that the potential is time dependent. Okay. Now, why this is a good estimate? So this is a good estimate. You see there is a very big difference. So k is positive. So this is rho is positive. Here rho is positive, and k is 1 over x to the d minus 2. So this is a positive term. And this is also a positive term. So this is always positive, and this is always positive. The problem is that sigma could be either plus or minus 1. And this creates difficulties. So if sigma is 1, we are in a very good situation. So now, if sigma is 1, then what you have is that, so the energy is conserved. So you have that E of t is equal to the energy at time 0. So if, let's say, this is bounded, then you have that the energy is bounded for every time. And so this implies, so the energy here is kinetic plus this potential term, k convolution rho t, 1/2. This is my energy. Now it's a sum. So this implies that both terms are bounded. So the first term tells me so that the integral of 1/2 v squared ft is bounded for every time. And the second term, what is this? This is the integral of k convolution rho t times rho t. Okay, but k, again, I have to be careful with signs. Yeah. So this is the same. So you have to remember that Laplacian of Vt is minus rho t in this case. So this is minus the integral of Vt Laplacian of Vt. So this is minus Vt. No, this is Vt and this is minus Laplacian. So you can write this in this term, and then you can integrate the Laplacian by parts. Okay, so this is, here is Vt. So you integrate the Laplacian by parts, you get the integral of grad Vt square when you integrate by parts. But grad Vt is minus the electric field, the force. So this is the integral of Et square. So the energy, in this case, E of t is nothing else than the integral of 1/2 v square ft plus 1/2 the integral of Et square dx. That is going to be globally bounded. And so for free, conservation of energy will give you some integrability in V and the fact that the vector field is automatically L2. OK. Now I would like to comment what happens when, so this is sigma equal 1. It's interesting to understand what happens where sigma is minus 1. And I think that will be everything for today because I don't have much time left. Well, so I will do it in dimension d equal 3. You will do something in dimension 4, and then it breaks down. So in this case, I have two competing terms. Okay, so I have the energy, which is bounded, is kinetic energy, and now I have minus this negative term. So I have minus 1/2 the integral of k convolution rho t rho t. So all the question is, OK, I know that the sum is bounded, but is it possible that this goes to plus infinity and it goes to minus infinity in such a way that the sum remains bounded? And I want to show you that under additional assumptions on f, this is not possible. So if I put some integrability on f. So the way it works is the following. So we have to understand this potential energy, which up to a sign is the integral of Vt rho t. So this is the potential energy, right? OK, so what do? We say, OK, suppose I want to make this integral finite, to find some bound. I would like this to be in 2 conjugate order exponents. So this is in some LP. This must be in the dual. So let's see. If rho t is in LP, this means that the Laplacian of V, which is rho t up to a sign, is in LP, which implies that Vt is in W2P. And in dimension 3, this embeds by Sobolev embedding in L 3P minus 2. By Sobolev embedding dimension 3. Is correct? Yeah. No, 3 minus 2P. Sorry. Yeah. Dimension minus twice P. OK. And now I want this, so Vt is in this space, rho is in this space. I want this exponent to be conjugate. So this means 1 over P plus the inverse of this, 3 minus 2P over 3P must be 1 to be dual pair. And this is true if and only if P is 6 over 5. That's what it is. So if P is in 6 over 5, this implies that Vt is in L6. This number becomes 6. And then you get the following, that the integral of Vt rho t is bounded by Holder inequality Vt in L6 rho t in L 6 over 5. So this is just Holder. Then by Sobolev embedding, this is bounded by the Hessian of Vt in L 6 over 5. So this is by Sobolev. I copy rho t, L 6/5. And now by elliptic regularity, the Hessian of V in LP is controlled by the norm of rho in LP because of the Laplace equation. Like the Laplace equation makes you gain two derivatives in LP spaces. So this one is controlled by a constant rho t in L 6/5. And so you end up with constant rho t L 6/5 square. Okay. Now, this means that I need a control in this space for rho t. How can I get this? I only have one information at my disposal. Well, I can trade two things. One, I could put additional condition on F, like Ft is in a very big LQ space. So on Ft, I can assume that is L infinity for the initial condition. Anyhow, this is propagated in time. Then I know another information that I could try to use some part of the kinetic energy. And this is what I want to do, to trade a bit of the information coming from the kinetic energy. So let me explain this, and which is, I mean, it's just a short computation, and then for today we finish. So let's try to estimate rho t of x at a point x. What is this? This is the integral in R3 of ft of x v dv. Now this is the integral over the ball of radius r of ft of x v dv plus the integral over the complement of the ball of ft x v dv. Okay? Okay, now I want, in this part, in the second part where v is large, I'm going to use the kinetic energy. So I multiply by v square, and I divide by r square. I can do it, right? And here I use Holder inequality with some LQ norm that I don't know yet. So I say, okay, let's assume that this is in LQ. So this is bounded by the integral over BR of ft to the power q dv, 1 over q, then the integral over BR of the function 1 in 1 minus 1 over q to be chosen. And then here, plus 1 over r square, the integral over R3 minus the ball, but I can put everything now, of v square ft of xv dv. Okay? Now, this, so the volume of the ball is r cube in dimension 3, up to constant. Then I have this power, 1 minus 1 over q. So this is bounded by constant r 1 minus 1 over q times 3. Times, here I integrate everything, integral over R3 of ft to the q, 1 over q, plus 1 over r square, the integral over R3 of v square ft xv dx. Okay, let me give two names to this. So this is dv. Let me give two names to these functions, just to be consistent. Yeah, so this function, I call it a of x. It's a function depending only on x, because I integrated already in v. And this function is b of x. Okay? So what I obtained is that rho t, so rho t of x is bounded by constant r 1 minus 1 over q times 3 a of x plus b of x over r square. Now, r is arbitrary, so you can optimize in r. You can choose the best r possible. So you do just optimization in one variable, and you get this very appealing expression. Rho t of x is bounded by constant a of x to the power 2 over 3 q minus 1 plus 2q, and then b of x to the power 3 q minus 1, 3 q minus 1 plus 2q. That's what it is. Okay, now I would like to do some order inequality to close the argument. But to do an order inequality, I will need that this exponent plus this exponent is equal to 1 to do some kind of order argument. Because I want to put then this function is L1, this function is in L1. So I don't have this here. So I have to raise everything to a power in such a way that this exponent plus this exponent is 1. What is the power? I give you the answer. So you just take rho t and you raise it to the power 3. So the denominator, 3q minus 1 plus 2q, divided by the sum of 2 and 3q minus 1. So 3q minus 1 plus 2. Sorry. And this is pointwise bounded by c a of x 2 over 3q minus 1 plus 2, b of x 3q minus 1, 3q minus 1 plus 2. Okay, so it's almost time. Actually, it's time, but 2 minutes, I'm done. So now this is a power exponent alpha, and this is 1 minus alpha. The sum now is 1. So I can integrate in x everything. So I get that the integral of rho t to this very ugly exponent, but that's what it is, 3q minus 1 plus 2q over 3q minus 1 plus 2, is bounded by constant, the integral of a of x to the alpha, b of x, 1 minus alpha. And now you can use order inequality on this term to say that this is bounded by constant, then the integral of a to the alpha outside, integral of b to the 1 minus alpha outside. I apply order inequality with exponent 1 over alpha here and 1 over 1 minus alpha there, their conjugate. Okay, and then we're done, because this means that here, what is this? This is the integral in the x of this is the integral in the x here. So here, a, what was it? Was the integral of ft to the power q. So this is nothing else than the double integral of ft to the power q dx dv. And this is the kinetic energy. This is the integral of v square ft dx dv. So I showed that if ft is in LQ and the kinetic energy is finite, then rho t gains some integrability, because this power is always bigger than 1. But now you remember that we need that rho t is in L 6 over 5. That's what I needed before. So you have to impose that this is 6 over 5. You compute, and this is equivalent to the fact that Q is equal to 9/7 numerology. Okay, so you write this equality in this particular case, and what happens here is that, so what discovered is that norm of rho t L 6 over 5, so the inequality I just proved in this very particular case, gives, let me just copy the exponents, it's going to be easier, is bounded by the norm constant, norm of ft in L 9/7 to the power 3/4, and the norm and the integral, so the kinetic energy, k of t, to the power 1/4. And this is crucial that I get 1/4. Because then what I'm left with, now so this is one inequality. Now you remember that I proved that the potential energy was bounded by the square of rho t to the 6 over 4. So this implies that the potential energy, so the integral of vt rho t, is bounded by the square of this. So ft L 9/7 to the 3/2, and then kinetic energy to the power 1/2. And now so this is the potential. So this means what? That the total energy, ET, which is what now? Kinetic minus, so minus the modulus of the potential, because they are opposite sign in our case. This is greater, so we assume that it's bounded. And this is greater than what? Then kinetic minus a constant. Now this is the L7 norm of F, which is propagated in time. So if it's bounded at time 0, it's bounded for every time. because every LP norm is propagated. So here I can put just the initial condition in n 9/7, 3/2, and then I get kt to the 1/2. And you see from this bound that the kinetic energy cannot blow up. If this goes to infinity, this goes to infinity much faster than this. They can never compensate. So this implies that k of t is bounded. And once k of t is bounded, this potential is bounded. And also the potential is bounded. So the philosophy was not, this will not be completely, I mean, it will be partly related to what I will do tomorrow, but the philosophy here was just that there are situations where sigma is positive, where you get for free estimates, where sigma is negative. You have to play with Sobolev embeddings a lot. And the worse is the higher is the dimension, the worse it gets. So it works here, dimension 3. You can do the computation dimension 4. You still get a Q. I think it's 2, something like that. And then dimension 5, this doesn't work. There is no exponent that is going to give you conservation, a bound. So then you see that the dimension really, everything breaks down in higher dimension. So I stop for today and apologize.